Welcome, Advanced Kentucky students and AP Chemistry students and teachers. This is Lew Acampora, as you know, and it's nice to see a good group here. The AP Chem exam is coming up in 3 days. So I just want to go over some things and give you some hopefully hints for doing as well as you deserve to do. And I think that most of the folks who've been participating in these meetings really deserve to do quite well. I think there's nothing to be afraid of. The College Board, I know, is going through extraordinary measures to make these exams valid and accessible and a good reflection of the years of chemistry. So one thing I want to start out with, and I'm going to go ahead and share my screen here. That, this is the official College Board, information for students website. And I know that I hope everyone's been aware of this, but there are resources that you should be, aware of. I'm only saying this now because the AP Physics Level C exam, that's a calculus-based course, was given this morning, and I'm on the chat room, and quite a few teachers have said that their students have been having problems. Some of their students have been problems with submitting their work, and I know there's a demo site where you can practice, but you've really got to make sure that your software is up to date. If you're using a smartphone, if you're using a laptop, it shouldn't matter. I would personally recommend using a laptop or something that you can keyboard, but do get on that website and make sure that everything is, and all your software is up to date. Because of exam security, you will only have one chance to submit it. If something goes wrong, you will have another chance to take the exam in June. But I imagine you'll all want to get that over with. So, on the College Board website, there are the exam day checklists, and this will go over things that you should have. Periodic table of the elements that you should have printed out. And that's important. I know most of your textbooks are going to have a periodic table of the elements, and there shouldn't be any math that you would need a calculator for on this exam. But if you're asked for a atomic mass, use the one that is given to you from the College Board. You can certainly supplement it, and most of you have seen this periodic table. No, it's a pretty bare bones table with just symbols. It doesn't even have the names of the elements. And you're free to have your book with you, but download that and make sure it's available in hard copy. You don't want to be swiping windows as you're taking the exam. And then the AP Chemistry equations and physical constants sheet. And I'm going to post these all on the AdvanceKentucky KY 2020 website for those of you who might not have a chance to get them from the College Board. You'll also note that there is a sample question that's been downloaded. I'm going to mention it today, but there are some very, very good videos of Mr. Faribaugh going over the answers to them that are on the College Board website. So rather than take time to do that, I will certainly be happy to answer questions now or later, but I would certainly refer you to that for additional practice. There are actually about 4 hours of videos for that, so that if you're looking for something to kill the time between now and the AP exam, that might be a fun way of doing that. Okay. Most of what I want to do today is to look at the mock exam questions that you all the students here took and all the teachers here presumably administered, and just with the idea of not going over these questions, but also saying how can students best gain credit for what they are writing. And this involves kind of acting as a score. So we'll go over the questions and their responses, and then I'd like the students and teachers here to score some some sample responses. Some of these are garnered from actual student data. They're anonymous, but if you do recognize your own in either a good or a bad sense, please take this constructively. But hopefully you will understand what you need to know. Before I do that, I also want to, I guess, show a study guide that I've prepared. And this is a best guess among myself and some of the other leaders of the exam as to what you can expect the exam to cover. It's going to be only 20 points available, and every point's going to be quite meaningful. But looking at the exam and what you might best be asked for, this is really where you're going to see the bulk of the questions. So I'm going to break this down as structure of matter, Coulomb's law and its applications. That really is everything underneath here relates back to charges, and it's important. And being able to refer to Coulomb's law specifically in your responses when asked to explain something. Atomic structure and periodicity. Is going to be what we mean by the electrons around an atom, because that's really the bulk of chemistry. Photoelectron emission spectroscopy, or PES, and you'll see one of those on the mock exam, but knowing what those peaks mean and where they come from. For covalent bonding, you should be able to draw electron dot diagrams that satisfy the octet rule. You should be familiar with hybridization and resonance. You should be familiar with bond strength and bond length and how that interacts, how they are related to the electron dot diagrams. Ionic bonding and lattice energies, and that's our preferred way there when we talk about the strength of ionic bonds, and intermolecular forces. And there are good videos from both the College Board and AdvanceKentucky on all of these. Chemical reactions certainly represents the heart of chemistry, and you should know, and everyone here I'm sure knows what we mean by a balanced chemical equation and having the same number of particles on the reactant side and the product side, but being able to represent that by either a molecular equation or a net ionic equation as appropriate, and what that means on a particulate level representation, where we, like as if you were building models, with balls and sticks for molecules and ions. Stoichiometry will undoubtedly come up, and that means using this unit of the mole and why it's important. And that things in chemistry happen in ratios of numbers of particles or moles of particles, not necessarily grams or milliliters. And then reactivity, specifically acid-base reactions, and you should be able to identify conjugate acid-base pairs, know what oxidation numbers are, and redox reactions. Moving on from there, calorimetry and thermochemistry is going to be one of the big topics, the energy of a temperature change or a phase transition. And this equation, Q equals Cp times M times delta T, which shows up on the formula sheet. Knowing what the heat of reaction means, that you can calculate from experimental data, and many of you probably did a lab involving this, that you can calculate it from the enthalpies of formation of the reactants and products, and that you can calculate this from bond energies. So, Professor John Gill, Oklahoma State, did a nice AdvanceKentucky review session on thermochemistry. Chemical kinetics is another big topic, and Ms. Clark from Bardstown did a very nice AdvanceKentucky review for chemical kinetics. Understand though what we mean by the rate of the reaction, the rate law, and the rate constant, and these really mean different things here. Be able to determine and interpret what the rate law is, and that especially is a linearization of graphs for 0th, 1st, 2nd order decomposition reactions. Be able to look at a graph and interpret what the order of the reaction is, and then to be able to pull off the value of the rate constant and the reaction rate from those graphs and from the slopes of those lines, and understand how you can turn any reaction into a pseudo decomposition reaction by having a large excess of all the other reactants. And then how does the rate law relate to the mechanisms? And again, there's a nice video on that goes over some sample problems. Chemical equilibrium is probably the heart of AP chemistry. And even though acids, bases, and the dreaded B word buffers will not show up on this exam, equilibrium is incredibly important if you go on in chemistry or biology. God, boy, most biological systems are striving toward a state of equilibrium. Fortunately, they never reach them until we die, and it takes a while. But the equilibrium state is one of those kind of special advanced topics. And why do systems attain equilibrium? Calculations using ICE tables, that's initial change in equilibrium concentrations. And then the interpretation of the equilibrium, the K versus Q and Le Chatelier's principle. And then the laboratory work and techniques that I think are likely to show up on the exams are, because they are common enough and most students would have gotten to them: spectrophotometry and Beer's law, titration and titration data, and calorimetry and delta H measurements. So that is a pretty good review, I think, of what you might expect. And if I were studying for the exam, the things I would review for. Moving on, I guess we want to go to, so I haven't checked the chat. Aaron is going, my co-host is going to chime in if there's anything that needs to be addressed. But I hope that most of you will remember this question. I'm going to look at some of these mock exam questions and ask you, the students and teachers, to score some sample responses. So, here was the first question. You were asked to answer the following questions about ozone. Now, you don't have to know what ozone is, and there's no memorization on the exam. But you're told the O3 molecule has a central oxygen atom bonded to two outer oxygen atoms that are not bonded to one another. And then you're asked to draw the Lewis electron dot diagram, and don't let terminology confuse you. G.N. Lewis was a prominent physical chemist from the early 1900s who came up with much of the theory of covalent bonding. And then for the ozone molecule, and include all valid resonance structures. And make sure you read the question thoroughly and take a hint from that. Now, it won't help if you don't know what resonance is or you haven't heard of it. But if you have, then make sure you answer the entire question. So here is a response that would be pretty good, very good. It would garner full credit here. And we have an ozone electron dot diagram. It's perfectly okay to draw dashes to represent bonds and understand that these are electron pairs. It's also certainly okay to, let me see if I can represent electron pairs by just lines like that instead of two dots. And then there's a lot of variation here. But what's the important thing is you've got to have the right number of electrons. And since each oxygen atom contributes 6 valence electrons, we should have a total of 3 times 6 or 18 valence electrons, which 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's okay. Every atom should satisfy the octet rule unless it calls for otherwise called for. In this case, we do see that this oxygen atom sees its 8 electrons, and this oxygen atom sees its 8 electrons, and this oxygen atom sees its 8 electrons. So this would be a perfectly good valid electron dot diagram for the ozone molecule, but because it's kind of, there's a broken symmetry. We have a double bond between the central oxygen and this oxygen atom on the left, and only a single bond to the right. And there's no reason that the double bond should have to be on the left. So we can draw this equivalent structure, not identical, but equivalent, with the double bond on the right-hand side. And the actual structure is a resonance hybrid or a mixture of these two, kind of an average. And this is what we mean by resonance structures. So you should be able to recognize that, and when it occurs, so that's our resonance. You might also be asked about hybridization, in which case the central atom would be sp2 hybridized, since there is one unshared pair and 2 sigma bonds. So these are things you might also look at. We also could talk about formal charges, and I'm not going to do that right now. So in terms of the scoring standards, the student would earn 1 point for a diagram that includes all 18 valence electrons and obeys the octet rule. And then a second point would be earned for showing the correct application of resonance. And we'll look at some samples in just a minute. Before we do that, the second part of this question asks for students to identify the shape of the ozone molecule based on the diagram that they drew in part A. So if a student had an incorrect diagram in part A, they could still get credit for part B, the shape of the molecule, if the shape was consistent with what they had shown earlier. So I'm going to come back here and now, whoops, come up with a new share. Here we go. And here's a sample student response. And congratulations if you were one of the students who sent this up. And I'm going to go up and open up a poll and ask all of you to go ahead and take a look at this and give it either 0, 1, 2, or 3 points. So the maximum number of points you could give would be 3, and the smallest would be 0. And remember, it's 1 point for a valid electron dot diagram that shows 18 electrons and obeys the octet rule. A second point for a correct illustration of resonance, and a third point for a shape that is consistent with the electron dot diagrams. And those of you who are clicking in 4 and 5 points, you're being overly generous, but that's really not possible on this one. This is a 0, 1, 2, or 3 point question. I'll give you a minute to look at that. And students who remember taking this, think about how you might have answered this and how you might answer it to get full credit. So we've got over 80% of the participants voting. I'm gonna not wait for the last few in case people are. Oh, and if you can't see your poll, if you go to the participants list and go to more, it should show up. It's possible that you haven't seen that. So I'm gonna end the polling now and show the results. And the overwhelming majority of participants, students and teachers, I think, gave this 3 points, and it should earn 3 points. I don't know, I assume the 4s and the 5s really meant to be 3s, but you're trying to give extra credit there. There are about 7 of us only gave 2 points, and that might be because the student didn't have a double-headed arrow in here. They were shooting that or that. But that's, I mean, we really are, the scorers, believe it or not, are really trying to give students credit where they deserve it and not take away points for I'd call technicalities. This isn't the law. So that's pretty good. And the almost 70%, and actually almost 80% if we count the 4s and the 5s, gave this the same score I think I would have. Here's one that's a little bit more challenging, I think. So let's go ahead and look at this. Oops, and I have to figure out how to open my poll. Whoops. Hang on a sec, okay. Sorry, I'm getting technically. All right, so. I'd like to have one more vote. There we go. We've got over 80% of the participants voting, and that's pretty good. So I'm going to end the polling here. And so we've got most of the participants, 71%, gave it this response 1 point, and I would go with that. We have a few nice, generous people out there, and it doesn't mean that's not a bad thing, but you are a little bit overly generous here. Remember, there was 1 point for a octet, for a good electron dot diagram that satisfies the octet rule. And in this case, even though there are the correct number of electrons, this oxygen atom does not satisfy the octet rule. There are only 7 electrons, and the same for this one. Only the central atom satisfies the octet rule. So this would not get a point for the first point, and there's no illustration of resonance, so we would not get the second point either. However, the student does earn a point for part B because the student mentioned that the shape is bent. So even though this is an incorrect electron dot diagram, and according to this electron dot diagram, the hybridization of that central atom would be sp3 instead of sp2, as it really is, would be in the correct electron dot diagram. They would still get credit for having that bent shape. Let's go ahead and look at the last one here. And I'll relaunch the polling. And ask you all to score this one quickly. And make sure you move the view window out of the way so you can see the entire. Okay, a little bit more of a horse race here. All right, nice job. I'm going to stop right there and say that 62% of you are right on target. This should get 1 point. I understand where you might be tempted to give a second point or even no points. I think that the electron dot diagram is correct. And sometimes it's very hard to just read, count the dots. And I remember I read these one year and I was about to take away, not award a credit, and I brushed my hand across the paper, and one of the things I thought was a dot was actually an erasure mark that stuck to the paper. So you've got to be careful. Hopefully that's not happening here, but this does have the right number of electrons and does satisfy the octet rule, so that would get 1 point. There is no resonance, so that second point is not eligible. And then the shape here, and this is something that confuses students frequently. When we talk about the shape of the molecule, we're really referring to the geometry of the atomic nuclei, or the atoms. And even though you might say the electron cloud is trigonal planar because this unshared electron pair would extend out here into space, you can't really see electrons with X-rays or whatever you're talking about. So we really are talking about the shape of the molecule, the nuclei, and this would be bent. So unfortunately, trigonal planar, even though I suspect the student had a pretty good handle of what they meant, this would not earn credit. And that's something you want to watch out for when you are answering this kind of question. The electron dot diagrams should reflect the number of electrons, but the molecular geometry refers only to the atoms themselves. Okay, so if there are any questions related to question 1, parts A or B, go ahead and type them into the chat box. Otherwise, I'm going to go and look at the published answers for part C. Hide that and come down here. So part C had a little bit of thermochemistry. Your students are given the decomposition of ozone into diatomic oxygen, given the value for the enthalpy of this reaction as negative 285 kilojoules per mole. And remember, this kilojoules per mole, a good question is per mole of what? Because this reaction involves 2 moles of ozone going to 3 moles of oxygen. Even though atoms are conserved, molecules are not. And is this a mole of ozone or is this per mole of oxygen? And the answer is neither. It's per mole of reaction. So this is saying that a mole of reaction is a conversion of 2 moles of ozone to 3 moles of oxygen. And imagine that happening Avogadro's number of times. You would use up in 1 mole of reaction, you would consume 2 moles of ozone and form 3 moles of oxygen. So, you know, this is sometimes even the older textbooks don't have this, but this mole of reaction is a very nice concept that makes things a lot more reasonable. The bond enthalpy of the oxygen, you're also told that the bond enthalpy of the oxygen-oxygen bond is 498 kilojoules per mole. And don't be confused by bond enthalpy versus bond energy. Sometimes those terms are used interchangeably, and they really, that's being a little bit fast and loose with language, but they could, in this case, it is justified. And remember that that's a positive number because this is the enthalpy or energy needed to break a bond. I, in fact, usually like to call this the bond dissociation enthalpy. And this is something that always tricks a good fraction of students up when they're asked this questions, dissociation. Because especially if you've come from a biology class where routinely biology teachers say that when you break that high energy bond in ATP, it releases energy. And this is nothing wrong with biology teachers, that's just the way they talk, but it's definitely not true chemically. And that what happens in that process is you actually form stronger bonds. So dissociation. So it always requires energy to break a bond. And in this particular case, if you were to write this, let me do this with my mouse. So that tells me that if I started with O2, and most of you might remember that this is actually got a double bond between 2 oxygen atoms, and I were to break that bond, and I would now form 2 oxygen atoms, and this is all in the gas phase, that I would have, so I'm going to get an oxygen atom and then another oxygen atom, and these are quite far apart. Then I would have to put in 498 kilojoules of energy for every mole of oxygen that took the break. So that's what that represents. Anyway, okay, moving on. The students are asked to calculate the average bond enthalpy of an oxygen-oxygen bond in O3, and essentially that means that the delta H of the reaction, this value here, this value here, comes from putting enough energy to break the bonds in O3 and then forming the bonds in the product side O2. So we could think about as breaking bonds, and that's going to be a positive, breaking the bonds in O3. And I'm going to put the 2O3 there, plus the forming, the energy of forming bonds in the 3O2 molecules. And they add up to be negative 285. I'm going to leave off the units here. I'm writing this with my mouse, which is not that easy. And I already know that when these bonds form, this is going to be 3 times negative 498 kilojoules per mole. So remember, because this is the amount of energy needed to break a bond, so when 3 of those bonds form, the change in energy would be 3 times negative 498 or negative 1494. Now, the only other thing I need to do is say how many of these bonds am I breaking. If we go back, remember that ozone had a central oxygen atom and then 2 terminal oxygen atoms. So there are actually 2 bonds in each ozone molecule. So I can say there are going to be 4 bonds that have to be broken. I'm going to put an X there, put a plus there, and write equals negative 285. And then when I solve that for X by adding this to both sides and then dividing by 4, I should get about 302. And there is my equation. So student responses, they would get 2 points for this. They would get 1 point for correctly determining the number of bonds broken in the reactants and the number of bonds formed in the products. And they don't have to write that. The question does not ask you to write how many bonds are in the product side or reactant side, but so you're going to be looking for these numbers 4 and 3 to show up. And then the second point here is earned for the calculation of the bond energies consistent with the bond counting. So, if you had an incorrect number here, if someone put a 6 there because they were counting atoms and not bonds, they would still get that first point, but not the second point. So that is the that was the scoring standards for this. And I'm going to go ahead and find my window here. Go back to my Zoom meeting and ask you all to keeping those scoring standards in mind. Again, 1 point for the correct number of bonds and 1 point for the correct bond breaking and bond adding. We'll go ahead and score this response. So this is either 0, 1, or 2 points. And if remember, the correct answer would be 302.25 kilojoules per mole. Okay, someone's giving it 3 points, and that you can't do that. Well, it'd be nice if you could. And you certainly can't give it 5 points, but that's okay. This was a little bit trickier. I think it's good that you guys are taking time and trying to find what the student may have done correctly or incorrectly. All right, we're kind of stalled here, so I'm going to go ahead and end the polling and say that, well, I think we are a little bit overly generous here. And you'll see the highest score was 1 point out of possibly 2. And some people were very generous and gave 3 or even more so 5 points. But this actually, this response, even though it looks like there's a lot of good chemistry here, wouldn't earn any credit. And there are 2 problems. The first, I think, and we'll point that out, and is that the student took the total bond energy, which they got to be negative 1780, and divided by 6. And that should really be divided by 4. they correctly got that they were breaking 3 bonds, or sorry, they were forming 3 bonds in 3 O2 molecules, but they were breaking 6 bonds, and that really should have been a 4. And so that even though they got one of them right and one of them wrong, there are no half points in AP exams, so they did not earn that point. And this is a very, very tempting value, but if you remember the way the equation was set up, go back to the rubrics here. The equation was set up so that the negative 285, which was the delta H of the reaction, is going to be, we're going to add to that 1498. So this should come over to this side of the equation as a positive number. And over here, it's been subtracted. So had this been a positive number, had there been a plus sign here, then this would have earned a point. And this is kind of tough because the student did a lot of things right and made 2 errors, but that turned this from a 2-point response down to a 0-point response. So don't you guys do that on Thursday. Let's go ahead and relaunch a poll here and let you score this one. And again, 0, 1, or 2. And I will say that I'm impressed with how, well, except for that last one, the majority was a little bit off, but you guys are doing a really good job. And I think this does reflect that you know chemistry and how to evaluate chemistry. So I'm hoping this is a little bit fun and useful as we consider what you'll be facing in 3 days and what other teachers like me will be facing in a month or so when we start reading these. And we will promise to give them all the consideration we can. And we do. Okay, let's go ahead and look at what we, and now you guys were overly generous last time, and here I will say that you're being a little bit stingy with your points because this is a correct answer, and you might go back, and I'll go back and just show you the rubrics here. Say that X equals 302 kilojoules per mole, and that's rounded off to 3 significant figures. And at this point, we're not going to quibble over the decimal points or rounding. I don't expect that that's going to be part of the scoring standards this year. And this is actually a correct answer, which is pretty, unless an answer just shows up with no justification. And the fact that this is a lowercase j is, we're not going to care about that. But they've got the negative 285 plus 3 times 498. It's written in the kind of reverse order. And so they've got the 3 there and the 4 there. So that's counting the bonds. And they've got the right answer. So this would actually be a 2-point response. So you don't have to write a lot to get full credit, but what you write has to be correct. I'm going to skip that one, and then we can look at this one. So sorry if you guys were looking at that. So take a look at this one pretty quickly. And see if you can not only score it, but find the, now clearly this is a wrong answer, but see if you can find the error that the student might have made. This is also why it is important as you write your exam that you do show where your work is coming from. You don't have to show a lot of work, But if a reader can figure out where you may have made an error, then you're much more likely to get credit for any good chemistry that you do write down. And most of you are going to be very good at writing chemistry. So let's kind of stop this here. And I apologize if I'm cutting you off before you have a chance to score it. But I think we're stalled out here, and we've got a horse race between 0 points and 1 point. And I would say this, well, I wouldn't say this is, this response would certainly earn 1 point. And that's right here, where, again, this is at negative 285 plus 1494. And they got, this is actually correct. The only error the student made was dividing by 3 instead of 4, because there would be 4 bonds, 4 oxygen-oxygen double bonds in 2 ozone molecules. Just to keep in mind, so I'm giving you each about a minute, maybe a little bit less time to score this. If you were at the reading, a good reader would read 60 of these in an hour, but not just 60 Part Cs, but 60 exams. It goes by pretty quickly, but the scores are very reproducible. So I'm going to pause on that one and solicit any questions about how that might be scored, or the content, or how to use bond energies. And again, the big misconception is, students think that breaking bond releases energy, and you're good biology students, but that's not chemistry. We always have to put in energy to break bonds, and when bonds form, they release energy. So Part D, I'm going to now go back to my screen here, and this was kind of the hard part. This was the hardest part, I think, of the mock exam, in that it involved kinetics, and that's one of those 3 topics that I think are going to be assessed punch above their weight class on this year's exam, because you're not going to see any questions on electrochemistry or acids and bases, and equilibrium and buffers. So I think you're going to expect to see thermochemistry, kinetics, and equilibrium show up quite a bit. And now we have a kinetics. So here's our kinetics lab, or kinetics question. It has to do with ozone still, and ozone can oxidize the bisulfite ion. You do not need to memorize the formulas of these ions. In fact, you're given the balanced equation. You're told a solution is prepared in which the initial concentration is 6.4 times 10 to the negative 4th molar, and it's much larger, and that's going to be important. So those of you who are not familiar with scientific notation, I hope you all do recognize that this number is actually 64 times bigger than that number. And then the concentration of ozone is monitored as the reaction proceeds, and the data are plotted in the graph below. And you see a graph where the concentration of ozone is decreasing over time, but decreasing in kind of a special way. And I hope that most of you recognize their integrated rate law, that we can say, if this decreases that way, it could be linear. That would mean something different. That's supposed to be a line. It could drop more sharply and then level out more quickly, and that would mean something a little bit different. So you need to be able to interpret these graphs of concentration versus time for decomposition reactions. And we'll see that because the concentration of hydrogen sulfide is much, much larger than that of ozone, this is what I would call a pseudo decomposition reaction. We flooded the reaction mixture with hydrogen sulfide. Okay, so you're told the data are consistent with the following rate law. Rate equals some constant times ozone, and they didn't write it, and you wouldn't normally write it, but there's an implied to the first power there. So based on the graph of the previous page, for 1 point, students are asked to determine the half-life for the reaction. And you should all, you should breathe a sigh of relief, let your shoulders drop when you see a question like this. Half-life is just how much time it takes for the reactant concentration to drop to half of its initial value. So, if we go back to our graph here, and we see the initial value is 1 times 10 to the negative 5th moles per liter. Half of that would be 5 times 10 to the negative 6 moles per liter. And the amount of time it takes for that to happen is 0.01 moles, it's 0.01 seconds. And be careful of the unit there. So that's, a half-life is an amount of time. Make sure when you're given graphs, I don't think that you're going to be expected to interpret very, points between lines here, because some of the students will be taking this on a cell phone and the resolution may not be all that great, but do be sure you're as careful as you can be as you read that. So you get 1 point for just stating 0.01 seconds. And I think most students got that, earned that point. Part 2, students were asked to determine the value of the rate constant, K1 for the rate law, and to include units for the answer. And this is one of those places where units do matter, and they're not always going to be the same. The units of the rate constant depend on the order of the reaction. For a first order reaction, and you can kind of guess that just from the equation here, that the rate is always going to have units of moles per liter per second, or this is only have molar per second, or per hour, or per some unit time. And the concentration will be in units of molar. So the rate constant here, in order for these two sides to be equal, the rate constant will have to have units of 1 over seconds, or reciprocal seconds, or seconds raised to the negative 1 power. And that's kind of a weird unit. It's hard to imagine measuring something in that, but it is consistent. So in this particular question, the rate constant, or they would have a value. You're given the formula, the half-life equals 0.693 over K1. And those of you who are in calculus or pre-calculus might recognize 0.693 as a natural logarithm of 2. So that's where that comes from. And from that, we just turn it around because we know the value for the half-life. So we get 0.693 over 0.01 seconds. And that is 69, and the unit there is reciprocal seconds. And we've rounded off to 2 sig figs here, but it would be certainly okay to write 69.3. And that's 1 point for the correct value, so that's 69, and 1 point for the correct unit. So just getting the unit there earns you one of those near and dear points. You could also look at this and say, well, what is the rate of the reaction? And you can't ask that question because the rate of the reaction changes. That's the whole point. But once you have that value of K, the rate of the reaction would be that value of K times the concentration of ozone. And you can interpret that from the slope of the line that would be tangent to this graph at any one point. So as I try to draw a tangent line here, I pick any point here, and now I try to draw a line that's tangent to the curve at that point. I'm not doing a very good job here, am I? The slope of this line is equal to the reaction rate at that instant in moles of ozone per liter per second. And those of you who are in calculus would recognize that as a derivative, and those of you who are going to be in calculus have something to look forward to. I'm not being sarcastic there. It really is pretty cool when you know it. Okay. So that's a question that wasn't asked, but you could have been. And then we go on, and getting back to chemistry, considering the relative concentrations of the reactants. Briefly explain why the data in the graph are also consistent with the following rate law. Rate equals K times ozone to the first power times hydrogen sulfide to the first power. And this has to do with what we had mentioned earlier about flooding and the fact that the hydrogen ion concentration was in large excess, was much larger than that, so that even though as the ozone concentration decreases by, well, from its initial value to almost 0, the hydrogen sulfide concentration decreases by the same amount, and that's non-negotiable. That's just a stoichiometry of the reaction. But its percent decrease is negligible. In fact, it decreases by less than 2%. So this concentration essentially remains unchanged. And that's what you would need to recognize for a point. And many of you might have done this lab spectrophotometrically when you looked at the decomposition of blue food dye by hypochlorite ion or bleach, or possibly by crystal violet in an excess base solution. So the key things here to earn that point is to say that the data are consistent because its value remains essentially constant. And you mentioning that it's present because it's present in large excess. And that's kind of a tough point to get. Not too many of the mock exam questions actually earn that point, although I hope they would now. And that was just worth 1 point. And then in the last part here, describe an experiment that could provide evidence to support the rate law given in DIII, and that is this one here. In other words, how would you figure out whether this exponent here is 1, or it could be a 0, which would be, or it could be a 2. In other words, if the reaction is, if this remains constant, then you can't really tell from this one experiment what the value of the exponent is. Can you design an experiment that would let you know that? And there are a couple of ways to do this. A couple of different experiments. One thing you can do is repeat the experiment with a different initial concentration of hydrogen sulfite. If the change in the reaction is proportional, then the reaction is first order. So if we go back here, and I'll try to line that up again. There we go, pretty good. If I now do the same reaction, but I've doubled this, still in large excess, but now its constant value is twice what it was before, then the rate would be doubled, because I'd have the ozone times this to the first power, doubling hydrogen sulfide concentration, doubling that would double that. If this were to the second power, if it were a second order, then a doubling of the hydrogen sulfide ion concentration would quadruple the reaction rate. And obviously, if it were 0 order, it would have no effect. So that would be one way to answer the question. Another might be to swap places and run the reaction with a large excess, not of ozone, not of hydrogen sulfide, but of ozone, and monitor the HSO3 concentration. Another way that would be very challenging would be to run the reaction with comparable concentrations of both reactants and then model it, and you'd really almost have to do a numerical calculation to do this. So we'll kind of skip that one, but those are probably the ways to do it. Again, these parts 3 and 4 were a little bit more challenging, but I think that students are certainly accessible, and many of you will be able to look at those. So let me, let's go and let you score a few of these. There we go. So this is a student sample. Now I've got the question here, and you'll remember this is out of 5 points. See if okay, I hope you can all read that. So I'll give you a little bit more time on this one, but see how you would score this out of 5 points. Remember, that's 1 point for part I, that's the half-life. 1 point, 2 points for part II, where you get 1 point for the numerical value of the rate constant and another point for the unit. 1 point for part III, and 1 point for part IV. And there's a little bit more reading to be done here, so I'll give you a little bit more time. And I will take this opportunity just to check the chat box. No, I won't. It's not here. Very good. There's a pretty good consensus here. I'll give you a few more seconds, and then we'll take a look at this. All right, so we have a few threes, a few fours, and a few fives, and that's pretty good. And in practice, if you're within 1 point of the kind of official score, then you're doing pretty well. This, I think, would have earned 4 of the 5 points. And this is certainly correct here. The student has the correct, this paper has a correct half-life of 0.01. And I think that's an S, although someone might look at that and think it's a 5. I read that as 0.01 seconds. For the second part, they have an answer here of 69.3, and that's a T to the -1. And this is one of those cases where there's so little to be, you really have to get it right when it doesn't, you know, the units have to be correct because it's really not a whole bunch that you're adding here. So that's got to be seconds, and you know, if a student were to put hours or days here, you've got to get the right numbers from the graph. So unfortunately, the paper shows some knowledge but doesn't quite get it. And then I think this point was well earned in part III. There is so much HSO3 minus in the solution that the concentration of HSO3 minus can be assumed to be constant, and therefore only the concentration of ozone would matter. And this is that's good enough. You could write that in different ways, but I think that says that so much and constant are key there. This also illustrates something that a lot of students tend to do, and that's omit the charges on the ions. And well, that might not get you in trouble here. The charge is a really important part of the particle, and there is a special place in AP chemistry hell for students who omit charges on ions. And then part D says, you know, you could take an excess amount of ozone and add a limited amount of HSO3 minus to a solution and track the concentration of HSO3. So essentially reversing the reaction, and that would work. I don't think it would be very easy to do feasibly, but it would be, it would certainly do the job. So that would earn that point. This paper, this response would earn 4 of the 5 points. Let's see if we can get one more in here. I'm gonna see if I can put, okay, there we go. Maybe do this one and then one more, and then we'll move on to the others. So again, the possible scores here are 0, 1, 2, 3, 4, or 5. And that's 1 point for part I, which is getting the half-life. 2 points for part II, 1 point for the value and 1 point for the unit, and then 1 point each for explaining in part III and part IV. But the scoring is anonymous, so there's no record of how you're scoring, whether you're a student or a teacher, so don't feel like you're being a bad person. No one's gonna know or care about this. So even if you think you're gonna be close, go ahead and put down a number. All right, so we've got about 60% of the participants voting. I'm going to call it cut it off there and say that most of you are pretty good. That even though there's a lot of writing here, unfortunately, there's nothing that would earn a point. And those of you who gave it 1, 2, or 3 points, I hope you're my secret Santas if it ever comes to that. But we'll just take a look at this. And even though there's a lot of interesting and possibly some good chemistry here, these responses don't really address the question. There's nothing here that says the half-life is 0.01 seconds, which is a straightforward calculation or straightforward answer. The value is wrong, and it's not consistent with this. And had the student had 0.693 over 3, then I think they would have earned a consistency point here. There's also no unit listed here. So this is the concentration of ozone at the half-life, but that's not what the question is asking for. And then part III doesn't really address the question. It's true that the order of the reaction would be 2 if this were the rate law, and there's an additional reactant, but the rate law is not the same. It is different. And then the answer to part IV is too vague to really be, given any credit. Mixing the chemicals together and determining their concentrations, you have to be a little bit more specific, or a lot more specific about what the relative concentrations would be and what you would monitor their concentrations versus time. Okay, I think we've got time for one more. And I want to look and see if it's, yeah, this one's okay. And this one, I went ahead and transcribed the responses, and you can see them in red here. So the handwriting was well, it was quite legible. It wasn't dark enough, so on my computer screen I couldn't really make it out too easily. So I did the best I could in transcribing this and then put it in red. So let's go ahead and score this one and see how you would have answered this. So again, 1 point for the correct half-life. I'm not saying they earned that point, but that would be the maximum. 1 point for the correct value of the rate constant, and 1 point for the unit. And then in III, answering that question gives it 1 point, and IV earns yet 1 more point.
Lew,
Yo.
we have a question.
Oh, okay, excellent. You almost woke me up there.
A student asks, what does the half-life have to do with the rate law, if any relationship?
Okay, that's a terrific question, and I will be happy to address that right. Let's just go through this one. Thank you, student who asked that question. I don't have my chat box visible, so I don't know who you are or where you're from, but I appreciate it. And all the other students might be thinking that or kicking themselves for not asking the same question. There's my chat box. Thanks, Noah. All right, let's see what we have here. And the consensus here is 4, and I think that's a pretty valid consensus. A few 3s, a 5, a couple of 5s, but let's take a look at this. So I think this paper, this response certainly gets 1 point for part I, 0.01 seconds. That's right. They earn 2 points for part II, even though you might quibble about significant figures, but we're not going to assess those on this part of the exam. So they get 69.3. And then the unit there is reciprocal seconds. And remember, that could be written in many ways. You could write that as 1 over seconds. Well, I guess, or second, those would be the 2 common ways. I don't think part III quite makes it. It says they correctly say HSO3 minus concentration doesn't affect the reaction rate, but they don't say why. And they really haven't addressed the relative concentrations of this. And then part IV, well, actually, I'm going to go back and say that this, I wouldn't earn a point here either. while you can run the reaction where their initial concentrations are comparable, and this is true, but all this would say is that the HSO3 is not in the rate law. It doesn't prove, but the question asks you to prove that this is the rate law, and that wouldn't do it. So that might be picking a few nits there. And some years this might garner credit, but I suspect more likely than not. So I'm going to revise my initial my initial score and score that down to a 3. Let me go to that question. I'm going to put up a whiteboard here. And so what, we talk about half-life, and what half-life means in general is the amount of time it takes to use up half of what you started with, or to have half of what you started with left remaining. So if we were to graph the concentration of something or the amount, now since in chemistry we really concern ourselves with concentrations, moles per liter, but as long as the volume's not changing, we could also use amount. And then we're going to graph how that changes versus time. And we're going to start up here somewhere at some initial concentration. And that means this right about here would be half of my initial concentration. That's supposed to be a dotted line, and that's my initial concentration over 2. The half-life is the amount of time it takes for this to get down to here. So there are a couple of things. Let's say we have a first-order reaction. And a first-order reaction is the one that we saw before. We've got this curve that looks like that. And that's, those of you who are in pre-calculus or algebra 2 might recognize this as supposedly an exponential decay curve. The reaction keeps slowing down. The reaction is going, and remember the rate of the reaction is really given by the slope of the curve, and because the slope keeps getting less, or technically the negative of the slope of the curve, because the slope getting less and less steep, the reaction is slowing down. So there's my half-life. One characteristic of a first-order reaction, though, is by the time I get here, I've got half as much left, but the reactions are going half as quickly. So a first-order reaction takes the same amount of time for every successive half-life, and it doesn't really show it here. But after one half-life, there'd be half the initial amount. After another second half-life, so 0.02 seconds, there would be half of a half, or a quarter of the amount left. After 3 half-lives, there would be a half of a half of a half, or 1/8 of the initial concentration, and so forth. And the fact that the half-life is constant is characteristic of first-order reactions. If you had a zero-order reaction, let me pick a nice color here. How about green? A zero-order reaction would be characterized by a straight line. And these are kind of unusual in chemistry. This says that the reaction chugs along at the same rate regardless of what my concentration of reactant is. Well, here's my first half-life. My next half-life would be the amount of time it takes to use up half of that, or to bring it down to here. And clearly this is much shorter, much less time than that. My next half-life takes even less time because I'm using up less and less stuff at the same rate. So for a zero-order reaction, you can't really say what the half-life is independent of the concentration. And then the other case that we might be concerned about is a second-order reaction. For a second-order reaction, it turns out that the graph is much more drops steeply at first and levels off quickly. And you might guess that for a second-order reaction, the half-lives get longer and longer. So I hope that did a good job answering your question, but usually you'll see half-lives are most important with first-order reactions, and most of you are probably familiar with talking about the half-life for radioactivity, and you'll hear about the half-life of carbon-14 or uranium-235, and these are always first-order kinetics. So, this is a typical kinetics question. A little bit more challenging than I find them a little bit more challenging. I think most students do. But if you're, there's a good chance to go and prepare for that. And again, they're really good lecture videos prepared by the College Board and by AdvanceKentucky, to go ahead and plug our own product here. That will help you. But kinetics is one of those things I would want to be prepared about, especially looking at a graph and being able to pull data off of that graph. Let's move on. So now on our mock exam, we had a 10-point question and 2 4-point questions. On your exam on Thursday, you'll have a 12-point question and an 8-point question, and they'll be a little bit longer and have some time constraints. And that's, for exam security, they really want to make sure that students don't have a lot of time when they're finished with the question. So don't be concerned if you don't finish all the parts. Do the best you can, and students will be at 5s even if they don't address all of the parts. Okay, let's take a look at the rubrics for this next short question. And this involves spectrophotometry. Students given a sample of copper sulfate that contains a solid impurity that's soluble and colorless. And that's kind of important. The student wants to determine the amount of copper sulfate in the sample and decides to use a spectrophotometer. Good choice. First, the student presents a calibration graph by measuring the absorbances of copper sulfate solutions of known concentrations. The graph is shown here. And then the student dissolves the entire sample of copper sulfate. Make this where we can see it all. In enough distilled water to make 100 milliliters of solution. And I hope most of you are thinking about, how would you do that? What piece of glassware would you use for that? And the resounding answer should be a volumetric flask. Then the student measures the absorbance of the solution and observes that it is 0.30, and there are no units there. Determine the concentration of copper sulfate in the solution, and that's part A. So that's really just a question of reading off the graph, and even though there's no mark right here at 0.30, it's exactly halfway, and this line hits all the points between the axes here at the so this is going to be halfway between there, so that should be 0.15. And on the official scoring standards, they should have the absorbance is 0.15 molar, or sorry, not the absorbance, the concentration is that's written badly. That should be the concentration is 0.15 molar. The absorbance is 0.3. But any value from 0.14 to 0.16 is acceptable. And I think that gives you a little bit of wiggle room. But really, what the tendency for students is to kind of just eyeball it and go for the nearest mark. And a student who wrote 0.1 or 0.2 would not earn credit there. The number of moles of copper sulfate that were in the impure sample, well, they're going to take this concentration, whatever concentration they had for part A, and multiply it by the volume. But have to remember that this concentration is moles per liter, and the volume here is 100, not liters, but milliliters. A 100-liter flask would be quite a large flask. I've seen them, but they're not very common, certainly not they're expensive. So you would need to divide that moles per liter by 1,000 and get 0.015 moles. And again, if a student had the incorrect answer for part A and were consistent, they would still earn that point for part B. Moving on, in addition to the number of moles of copper sulfate calculated in part B, what other quantity must be measured, not calculated, but measured, in order to calculate the mass percentage of CuSO4 in the impure sample. And yes, you would have to know the formula mass of copper sulfate, but that's nothing that you would measure. That's something you would either add up or look up. What you would need to know would be the mass of the sample. And you've got to be very careful here. It's not enough to say mass or mass of the copper sulfate. You need to say the mass of the initial sample or the mass of the impure copper sulfate. And then, and I love these questions, although students don't do as well as you would think on them. They're asked to draw a particulate level drawing of a copper ion surrounded by water molecules to show the most likely orientation. And remembering that a water molecule is polar, and the oxygen atom, our little Mickey Mouse here, has a partially negative charge, and the hydrogen atoms are both partially positive. Since the copper ion is positive, the negative ends of the oxygen ends of the water molecule should be attracted to the copper. So you would want to show this, and it doesn't matter if they're at 2 o'clock and 7 o'clock, or above and below, or left and right, or kind of to the same side, but you would have to have that correct orientation. So those are the ways to earn 4 points on that on this question. Let's maybe take a look at some student responses. I think these will go pretty quickly. So let's go ahead and look here. Oops, I lost my cursor. Oh, there it is. So go ahead and score this, and this will be out of 4 points. 1 point, that's easy, 1 point for each part. And think about how you answered this question and how you could have answered this question, and possibly what silly mistakes you made. And we've got almost 2/3 of our participants chiming in here with a score. So I'm going to end the polling here. I'd like to get one more response. There we go. Okay, and I think the majority rules on this case. It's not always the case, but there are 2 points here. Someone who's a couple stingy folks out there, and then some generalists and very generous people, which is not a bad thing. But I think this is a 2-point response. Again, this is what we mean when we say you've got to really, when you're given a graph, don't just kind of wave your hand at it. Really try to read it as accurately as possible. And the scoring standard said anywhere from 0.14 to 0.16, but 0.17 doesn't quite do it. So no point for part A. Part B does get a point because they correctly took the incorrect value from part A, but used it correctly to get 0.017. Several responses from mock exam had students who put actually 17 moles per liter by forgetting about this 1,000 and just multiplying by 100. And while it's possible to get 17 moles per liter of something, you cannot get 17 moles of copper sulfate into 1 liter of anything. So part B does get a point. Part C has the word mass, but not mass of the impure sample. And you've got to be more specific here, because the total mass of the copper sulfate, the pure copper sulfate, is what you'll get from the spectrophotometry. What you need is a denominator. So this really, for credit, you need to write the impure or the initial sample here. Impure. So no credit here. And then this last part does show a nice diagram. I know you could kind of say, well, it looks like there's a covalent bond there between I'm not sure that these would overlap like that, but I think that they've got the answer and the correct orientation. So that would earn a point. That's a good 2-point response. these go by pretty quickly, so we'll do a couple more of these, and I'll let you kind of read that one. And these are very, very good responses, by the way. So if you took the mock exam and you're thinking, oh my gosh, I didn't really know what the question was asking, don't, you still have a good chance of doing quite well on the AP exam on Thursday. I think out of 20 points, my guess is that a student who earns 9 of the 20 points will score a 3. So that's less than half, but we won't really know until the scores are, until the papers are read. That always happens that way. As you're all seeing, once you've kind of looked at these standards and kind of internalized them, these papers go much more, they read pretty quickly. So we're already at almost 2/3 of the people scoring. So let's go ahead and take a look at the results here. And I think that we got everyone giving either a 2 or a 3, one kind of stingy person out there. You know who you are. I don't know who you are, but that's okay. And this should be a 3-point question or a 3-point response, 3-point answer, I guess. They did not get this point here because that's the absorbance, not the concentration, but that number was used consistently here. And then, excuse me, part C, the initial mass of the impure sample. And then this is a pretty good diagram here. So no point for part A, parts B, C, and D would earn credit. And I'm going to skip that one. That was actually a 4-point question. And I think actually that was the other one. So I think you guys have seen a pretty good job there. Some illustrations. And I want to close by quickly going over the last question that you saw in the mock exam. And this is something that's kind of new. Well, not new to you because you've just taken the course for 1 year. But if you've taught AP chemistry for a long time, and I have, then this photoelectron emission spectroscopy is a little bit new to the syllabus, and it really kind of emphasizes that there is empirical data for all these electron configurations, and all of chemistry is really interesting because the atoms have electrons that are not all just kind of in one lump place, but they occupy these shells, and all the chemistry of these different elements depends on the arrangement of electrons, and most specifically the valence electrons. How do we know this happens? Well, the empirical evidence is that you can measure the energies of these electrons in the atom, and we call this the binding energy, the energy that the electrons are held to the nucleus with, and that's a reflection of the Coulombic attraction between the nucleus with some number of positive charges and the electrons that are out here. And the actual binding energy depends on how many protons are in the nucleus and how many electrons are out there and where those electrons are. So you may very well be asked to interpret this photoelectron spectrum. Students, usually when these questions are given, they either do very well or very poorly, and I think that depends on whether they've actually covered this in class. And they really shouldn't be that challenging. So let's take a look at this one. You're given this binding energy, and this is a logarithmic scale, so, and with the bigger numbers to the left, and this tells us the larger the binding energy in megajoules per mole, that's a lot of energy, the harder it is to remove that electron, or the more strong those electrons are attracted to the nucleus. So if we go from left to right, we're always going to see the most tightly bound electrons, and this is going to be the 1s orbital, and then the 2s orbital. And the other thing is the height, how high are these peaks, and that corresponds to the relative number of electrons. So since this goes up 2 units here, we call that 1s2, and the College Board is really pretty nice about that. That should be an S, a 2s2, and then over here we've got a 2p subshell, and since this peak goes up 1, 2, 3, 4, 5, 6, we have 6 electrons in there. And then we have 3s would be our next subshell with 2 electrons. And then 3p, and this peak goes up 1, 2, 3 notches, so a 3p3. So we have a total of 2 plus 2 plus 6 plus 2 plus 3 is 15 electrons. And that means we'd have 15 protons. That would make it phosphorus. And you could really read off the electron configuration from the graph, from the PES spectrum here, or just work it out from the diagonal rule. But this is going to be the electron configuration. And that's hopefully 2 fairly easy points. If a student miscounted or misidentified the element, but got the correct electron configuration, either of phosphorus or of the element they named, they would still earn that second point. And then part B, let me clear that drawing. You have to say wherever you are on the periodic table. So, we're over here. So here's the periodic table, and phosphorus would be somewhere right underneath nitrogen, right here. So you're asked to consider the element directly to the right of the element identified so we're take a step to the right here. And what happens as we go across the periodic table, left to right, is that we add a proton to the nucleus, and we add an electron, and that extra electron is going to be in the valence shell. So how would that change this photoelectron spectrum? And we'll say, well, if we had sulfur, first of all, now sulfur would have a 4th electron in the 3p shell, so this peak would be higher, but it would also be attracted more strongly to the nucleus. So it would come up, not only would it come up a little bit higher to the 4th level, oops, I'm gonna have to erase that. But it would be slightly more strongly attracted. And sometimes there are aberrations out here, and I'm not actually sure of this, because when you start to put in a 4th electron to a p subshell, you're putting 2 electrons in the same orbital. So sometimes that will actually raise the energy. But that's not what we're asked for here. They're asked for the 1s peak. So because the 1s peak would be more, it'd still have 2 electrons, so it would have the same height, but now it would be more strongly attracted to the nucleus, because now the nucleus of a sulfur atom has 16 protons instead of the 15 protons that are in the nucleus of a phosphorus atom. And that would shift this peak to the left. So, and then you'd not only have to say that, but you'd have to be able to explain it. And for 2 points, you would need to say, first of all, the peak would be to the left of the peak in the spectrum. And that's pretty much all you had to say. So you could guess, but I wouldn't recommend relying on guesswork too much. And then you would have to, for the second point, you would have to tie that to the number of protons, not the number of electrons or the extra valence electron. It's the number of protons that matter. Now you could mention that there are also more electrons, and that would be fine. It wouldn't be wrong. But in order to earn credit, you would need to specifically talk about the number of protons. So with that in mind, let me bring up a couple of samples here and let you see what was written. So we'll just look at a couple of these. They'll go by, I think, pretty quickly. I'll go ahead and launch a poll, and you can write down what you think. So this is a 0, 1, 2, 3, or 4 points. And we'll do it both A and B together here. All right, so I think we've got a consensus emerging here that this is in fact a 4-point response, and I would agree with that. You know, the student correctly identified phosphorus, and it's enough to, since they were not asked, it's enough to either write the name of the element or the atomic symbol. Students are asking, you know, does spelling matter? And then it's nice, but we would not care as long as it's recognizable as phosphorus. So it's hard to imagine how you would misspell it. Oh, no, it's not hard to imagine how you'd misspell that. I've seen many British, you know, or different ways of doing it, but that's fine. It's not real legible, but this is clearly 1s2, 2s2, 2p6, 3s2, 3p3, so that's correct. To the left, that's all you really need to write for part B. And then there'll be more protons in the nucleus, and that really is enough. And you could read on, and all of this is okay. This response talks about the electric force between the nucleus and the 1s electron pair would be greater than phosphorus because the element would have more protons. They never identified that element as sulfur, but that was not part of the question. So this is going to be good for 4 points. Here's one that's a little bit more interesting. Spoiler alert, well, not really, but this is not going to be a 4-point question, and you probably know that because they misidentified the element. So they can't get that first point, but see if there's anything they can. Can you find a point in that writing there? A point, I should say 2 or possibly 3. I already told you it's not a 4-point response. All right, so look at this one and then maybe one more. Most of you end up with 0 points, and that's being a little bit strict there. This response would actually get 1 point because even though they did not get the element correct, this is the electron configuration for sulfur. And it's okay to write the shorthand, neon, that core 3s2, 3p4. I suspect the student just didn't look very closely at the height of that last peak. So, you know, having misidentified the element as sulfur, you don't want to, you know, have them inflict double jeopardy by, look, I can do that, by double penalizing for really what is one mistake. So and this is a good lesson for students that you know, it's not, if you make a mistake, but you're consistent with it, you're still going to earn credit. Unfortunately, there was nothing earned in part B because they say the same position, and even if they were talking about sulfur and the element to the right of sulfur, which on the periodic table would be chlorine, it doesn't really matter what element was chosen for part A, unless a student put a noble gas for part A, in which case I don't know what would happen because there is no element to the right of the noble gas on most periodic tables. So, but once you say the same position, that's going to not earn credit. Even though it's the same, the students can be thinking that it's the same electrons and therefore it's have the same energy. But remember, the energy of those electrons depends on the charge on the electrons and the charge on the nucleus. And there would be a different number of protons in the nucleus. Okay, that one back there is a really good one. So they're terrific, but they're kind of boring. Let's close up with this response, which is interesting, I think. All right. So we're going to finish strongly, I think. And most of you scored this as 2 points by a healthy majority. I think that's absolutely valid. It's close. I had to read this and wondering what this as, but realized that this is actually the atomic symbol for arsenic. And so the person is looking, they're unfortunately one row too low on the periodic table. So this is incorrect. The electron configuration is also incorrect. First of all, you should never use anything except a noble gas here. But even if you were, this is missing the 3d10 electrons, and then that should be 4p3. So if you go ahead and you work out the 4p3, 4s2, so if you actually go ahead and work out the electron configuration for arsenic, it would have an argon core. And even though you might be tempted to write calcium here because this would correspond to calcium, never ever do that. You want to show all of the electrons outside of the noble gas configuration. But part B is actually quite good, even though the vocabulary might be a little bit non-traditional. It's hard to say would be, it's 1s peak would be to the left, and that's good for a point. Because not only is a stronger nucleus, and yeah, I'm not thrilled with that. I hope, the student would be able to say what they mean a little bit more clearly, but by stronger nucleus, I think it's pretty clear that the student means has a greater positive charge in the nucleus and can apply a stronger attraction to its electrons. And the rest of this is actually true, but really irrelevant. But they checked both boxes there and would earn 2 points. So that's pretty good. Okay, well, I feel free to chat in if there are some questions about those. Again, we know these questions are not going to be on Thursday's exam, but questions like them will be. There are lots of resources out there from the College Board, from AdvanceKentucky. As I said, the first AP exams, not chemistry, were given this morning, and it looks like a pretty significant number of students might have had difficulty submitting their work. I really encourage you to get on and use the demo site and make sure that your software is up to date, that you can get the credit for that you deserve. And I think certainly if you're still on this after about an hour and a half, an hour and 40 minutes, you have tremendous stamina. I've enjoyed this. I hope to see you all. If you if you're at college and you see me around, say hi and remind me how I know you. But good luck to everyone out there. And if any questions come up today or tomorrow or even Wednesday, contact your teacher or contact me. I'm Lew Acampora at kscc.com. And good luck to all of you. So seeing no new chats, I will end the meeting here and wish you all luck. So bye-bye now.
Bye, Lew. Thank you.
You're quite welcome all. Bye-bye.